All right, so I mentioned Rust is better than C for security, and so let's find out why. So you can install Rust, and I'm using Kali here, just because a lot of you had it, and I was able to install the Rust compiler, I think, in this. So we'll make Hello World. So I'll do nano. All right. Right, I'm going to make a directory. Make a directory, Hello World. And CD. All right. It didn't get rid of all the stinking colors, unfortunately, but you can see it somewhat in this projector. I don't know a better way to get rid of all the colors in a bash session. Kali turns on all these goofy things that get in the way. It will be pretty hard to read in the video, but at least you can see it in the room. All right, and so here's the simplest Hello World program in Rust. And Control plus doesn't work, and Shift Control plus doesn't work to make it bigger, but anyway. So you see, it's a lot like it would be in C. You have a main function, and you have a print command with that funny exclamation point. All right, and then you compile this thing with Rust C. Aha, okay, command plus works, fair enough. So, Rust C, hello. All right, it compiled and you run it, and it says hello world. So that just shows that Rust compiler is working, and now we can play games like integer data types. So this will make a new directory for it. The tutorial I followed when I made this stuff made a separate directory for each app, like a modern app with many components, although that's not really necessary for these simple things we're doing here, but I'm just following it. So nano int $rs. All right, so here we go. This is an example of how integer variables are handled in Rust. You can define a variable without specifying the type, or you can specify a type, and this is an unsigned 32-bit variable. And then I can print them out, and if I compile that, it won't let me proceed because I tried to put a negative number in an unsigned variable, and you can't do it. And this is an example of, like I say, C will not do this. You can put something in, it will just cheerfully take the wrong data and put it in. For example, a string. A string is a set of 8-bit integers in C. You shouldn't really be putting characters in any of them. It's garbage. But this hypnotized me into thinking that a character was equal to an 8-bit integer, which it emphatically is not, especially when you go to Unicode. And that took me a long time to unlearn when I went from Python 2 to Python 3. Python 2 and C both do this weird thing of using 1 byte per character, which only works for ASCII, and it doesn't make any sense because there's a lot of non-ASCII, non-printable characters, like above 127. They really should be 2 separate data types the way they are in Python. Anyway, and Rust does it that way. So you define the data type, and that's one thing that can go wrong. So now let's try adding some numbers. And we'll see another interesting thing about Rust. So this is going to be, oops, I better do this in 2 stages. There we go. This will create the file. And this is the contents of the file. Okay, so now I define a variable, then I add one to it, then I print it out. And when I compile this one, again I'm in trouble because by default variables are immutable. So you can't change it. You can't add one to it. If you want to make it mutable, you have to put mut in there. And again, at first this seems like a waste of time, but they've done surveys, and like 98% of developers say the language they most like to code in is Rust because it's so easy. You fix it, errors don't proceed to production. If anything's wrong, it tells you and you fix it, which is really much better than having C where it will just cheerfully do the wrong thing and go to production, and you find out later it's wrong. So anyway, all right, so now let's do the integer overflow, and we'll start by doing it in C. So let's go home and nano ovc.c. All right, so here's an integer overflow. I define a variable 230, and then I have a loop that just keeps adding to it and printing it out. and that's an unsigned character variable, which, as I mentioned, makes no sense at all. How can a character be 230? But it is in C, because its whole concept of characters and strings is pretty bad and not really very accurate. So you can compile this thing with GCC for the output in OVC and the input from OVC.C. There we go. All right, now I can run it, OVC, and so it takes X, it adds to it, and then it just wraps over and gets small and gives you 2. So you add something to 251, but it goes to 2 and 10, that's C for you. And so how is the developer supposed to understand this? You make it bigger, and there's a bunch of vulnerabilities caused by this, like to try to limit you to input less than 50, and all you have to put in is like 65,000 plus 50, and you get past it because it wraps around and thinks it's negative, or 32,000 depending on the variable type. And this does not happen in Rust. Here's the Rust code to do the same thing, except instead of using a character variable type, we use an unsigned 8-bit integer, which is what C really means by a character. We set it equal to 230 and add to it over and over, compile it, and run it. And it adds up until it gets big, and then when it was going to wrap around, it crashes and said, nope, attempt to add with overflow. So it won't just give you the wrong answer, instead it will tell you what you've done is not working, which is much friendlier to the developer. So that's a good one. Then we can try string overflows, which we just did in another context. And so nano strov.c. All right, so here's another simple string overflow. I define 2 characters, 2 variables, and then I just input a new value from the user for one of them, and then print them out again with addresses and contents. All right, so I compile this one. All right, and then whoops. Oh, I didn't put a C at the end. Okay. Fine. Okay. Okay, so now I run it. Now I put in CCCC, everything's fine. But if I put in too many C's, I should get an overflow. And the overflow is string 1. So I enter new value for string 2. Now, up here when I put a new value for string 2, string 1 stayed the same and string 2 changed to C's. But here I put in a new value for string 2 and string 1 changed. Again, how is a developer supposed to cope with this? This is madness. Put in a value for one string and a different string changes. This is very cruel. And it doesn't happen in Rust, of course. If you try this in Rust, this is the same program in Rust. Remember, I had to make mutable strings because I'm going to be changing them. So I compile that, Rust C. Okay, warning, but not a crash, so I don't really care about it. And then warned me about it, it didn't change this one, and it didn't need to be mutable. So that's harmless, but it's in principle not quite right. And I can run this one, and so now if I put in CCCC, it just adds that to the existing A without changing B. And if I put in a whole lot of C's, it doesn't do anything wrong. It adds them to this one, it doesn't change that one, just like it should. And I put it with the minus G, so you can debug it easily, and it's in the project, I won't do it here, but if you debug it, you'll see how it works. The addresses of those strings don't change, but it's double indirection. What's in that address to those strings is a pointer to another location where it stored it, and that changes. It just moves to another location with enough room when it gets bigger, like it should have, instead of overflowing and causing the buffer overflow disasters. So that's, I think that's as far as this one goes. Oh, then there's command injection, I should mention. You know, if you write command injection, where you actually execute code that came from the user in C, then you get command injection. And of course, Rust can't save you here. I mean, that's not a binary flaw. you can do it with C, yep, here you can do it here. If you do the same thing in Rust, you can run a ping with data that came from the user, and it's not going to save you. It's not going to prevent that. That's a higher level flaw. All right. And I have another one here for some other things like dangling pointers and memory leaks and such. You can, and double free and things like that, and you'll see how Rust avoids that. As Caitlin mentioned earlier, when you allocate in C, you have to malloc, and then you have to free. And in Rust, you don't. You create it, and it notices your context by the curly braces, and when you leave the section of code that's using it, it automatically frees. So it always happens only once. You can't forget to do it, and you can't actually do it twice, both of which are serious flaws in C. And he has heap overflows in Rust, but those don't overflow as they would in C either. So, it stops a lot of these memory corruption vulnerabilities, and that's why the strong advocates say you should use it. So you might want to try some of those tricks. Get to know and love Rust.